Welcome to qnawire.
So in this problem, we're given 6 conditions. We need to sketch a graph that meets all 6 of these conditions. So first of all, we need to figure out what kind of scale do we what kind of graph do we need? Do we need positives, negatives, a mixture of both? For both the x and the y. So we see here we have x going to negative infinity and x going to infinity. We're going to need both x going in both directions. Second thing we can look at is the y's. We know that we need a y of 0, we need a y of 8, and we need a y of 5. Otherwise, we don't appear to have any need to have a negative y value. So we can kind of just leave the negatives, not quite leave them out, but we can focus on the positive y's. Certainly this graph could have negatives. We don't know, we're just sketching a graph. I should make this easier rather than harder. So that's step 1, is to figure out a rough scale. And our x's probably won't matter too much, but I'm going to give us a scale in our y's. So we have 8 up here, we're going up by 1s. 8 there, we have 1, 2, 3, 4, 5 there, and 0 is on the axis. This is our y, and this is our x. So these are the 2 big numbers that we know that we need. We know that when x is 2, we're going to have an inflection point right here. We know that that is going to be an inflection point. What is an inflection point? That means we're switching from concave up to concave down, or vice versa. We are switching concavity. So those are some points that we know. We also know 2 things about what's happening as we go towards infinity and negative infinity. As we go towards negative infinity, we have a horizontal asymptote at 0, meaning that we're going to get really, really close to the x-axis, but we're never going to touch it as we approach negative infinity. As we approach positive infinity, as x gets really, really big, we're going to start approaching 8, but we're never quite going to get to 8, but we're going to get really close. So I kind of sketch in 2 dashed lines there to remind myself that's about where we're getting to. So then from there, we have some general guidelines for our graph. And now we start to look at the first and second derivatives and see what those tell us. First of all, this first derivative tells us that f prime, the first derivative, is positive or greater than 0 if x does not equal 2. This means that our graph is always increasing, except maybe at x equals 2 something else happens. At x equals 2, we may have a vertical tangent, meaning we have an undefined f prime, or we could have an f prime that is equal to 0. We don't really know. They don't really tell us. We might just have to wait and see what we come up with for that. Then we know 2 things about our second derivative. Our second derivative tells us about concavity. So if we are positive, like with this second condition, this means we are concave up, meaning our graph is pointing up like a U. A U is concave up. If we have a negative second derivative, like we do when x is greater than 2, that means that our graph is concave down, meaning it's opening downward, like an N. So, knowing that, we can kind of start to maybe build a mental picture of our graph. We know, so we're coming from negative infinity, we're coming from pretty darn close to 0. And we're increasing, we're getting bigger and bigger as we go. We're concave up, meaning that our graph should kind of be curving, pointing upward. If we imagine spilling water into this, it should be collecting in this area. So we're increasing, we're approaching this inflection point. We know that we go through this point because we have an inflection point there. We can't have an inflection point if our graph isn't going through that point. So kind of coming through here, the graph might get really, really steep right at that point. Perhaps that's why we have this x does not equal, or when x isn't 2, when x doesn't equal 2. Perhaps that's why our derivative isn't increasing there. We have a vertical tangent, which means it's undefined, meaning it's not positive. So we come to that point, and then we remember we have an inflection point, and we're switching concavity. These 2 points kind of tell us the same thing. At x equals 2, we're switching concavity, going from concave up to concave down. And then we kind of approach 8, and we stay really, really close to 8, and we continue on. So this might be an example of a graph that meets all of these conditions. If we just want to double check, our graph is always increasing. This spot on my sketch is a little bit weird, but it's okay for sketches to look a little bit weird because they're just sketches. We're just getting the general feature. So we're always increasing. We're concave up when we're less than 2 over here. We're concave down over here. We have an inflection point right at this point, 2, 5. As we approach infinity, we're approaching 8. And as we approach negative infinity, we're approaching 0. So we met all of our conditions. This is one example of a graph that might meet these conditions.